All right, so chemistry was the first unit in this course. Okay, and yes, it was a long time ago, so we need to go over a few things to kind of remind ourselves, what do we do in that unit, what's important, okay, and how do we do some of those important things. Okay, hopefully you guys had a chance to go over some of your chemistry stuff over the weekend. Okay, so the first thing we went over, okay, that's going to be on the test is naming compounds. Certainly we went over like the history of the atom as well, but it's just not as big a deal on the final exam. Okay, like I think there might be one multiple choice question on the whole final, okay, about like the history and structure of the atom. So if you want to peruse that lesson like once in your notes, you're probably good for that. Okay. But naming compounds is important. Why is naming compounds important? Because you can't do anything else in the unit if you can't do that. Okay? You can't write a chemical reaction. You can't properly balance a chemical reaction. You can't predict the products of a chemical reaction. You can't do a mole equation calculation if you can't do this. Okay? This is a fundamental skill that is required for chemistry. So, quick review. What are the two kinds of compounds we went over? Ionic and molecular. They have different rules for writing their formulas and writing their names. Okay? Remember that an ionic compound has one metal, that's something from the left-hand side of the periodic table, and a non-metal, that is something from the right-hand side of the staircase on the periodic table. Okay? So, quick review on naming the compounds. Okay? You will want to, for an ionic compound, the prefixes are not on the formula sheet. No, I expect that you know those. So yeah, make sure you know. So for an ionic compound, we write the name of the metal first, and we write the name of the non-metal second. Okay, so if we are looking at, let's say, this compound. Okay, I would write the name of the metal, Ca stands for calcium, and I would write the name of the nonmetal, and it needs to end in I, calcium chloride. No prefixes in an ionic compound, not ever. Okay. Exceptions that can come up for naming ionic compounds could be if you had a compound like this. Why is that one going to be different? That is exactly why. Copper has more than one possible charge. It is a multivalent metal. Okay? So we have to look on our periodic table and see what the charges are. They are 1 and 2 positive. So when I'm writing this out, I first have to figure out, is it the copper with the 1 plus charge, or is it the copper with the 2 plus charge? Okay? So the way I do that is I look to my non-metal. Fluorine's charge on my periodic table is always -1. How many fluorines are there? 2. So how many negative charges are there? 2. Okay. Every ionic compound has to balance its charges or have a net charge of 0. That means the charge on copper must be +2 because there's only one copper here to get it from. So this is copper, Roman numeral 2, fluoride. Okay, that's the ones we use the Roman numerals for. Okay. If I am writing the name of a molecular compound, then I'm going to need prefixes. So if I have, let's say, N2O3, right? What's the prefix for 2? Di, right? Okay, so dinitrogen. And what's the prefix for 3? Tri. Dinitrogen trioxide. Still the second element always ends in I. Okay? All right, one last possible difference with an ionic compound could be if I were to get something like this. This would be like the extreme case. Okay, so that ionic compound has both a multivalent metal and a polyatomic ion. Okay, how do I name polyatomic ions? Just copy it down from the chart. Exactly, you've got that box labeled Table of Common Polyatomic Ions. Okay, at the top of your periodic table, just write however the name appears in there. You don't change it to I, you write it exactly as it appears in there. So this is going to be iron with a Roman numeral, we don't know which one yet, nitrate.
We have to memorize all the special
Polyatomic ions?
yeah.
No, they're all on your periodic table. Right, they're in that box at the top. Okay, so no, you don't have to memorize it. And you don't have to memorize the metals either. All you have to do is look at your periodic table and see it's got 2 charges. Okay, so now I'm going to go back and figure out what Roman numeral needs to go here. The charge on nitrate is always -1, and there are 3 nitrates. So that means I've got 3 negative charges. They need to be balanced by my single iron atom. So that means this iron must have a charge of +3, and as a result, this is iron Roman numeral 3 nitrates. That would be as tricky as they would get for you. Okay, where are you going to see naming compounds on your final exam? There's a couple of multiple choice questions about naming compounds, but most importantly, it's in the written. Okay, the written response part of the final exam that has to do with chemistry, set up almost exactly the same as your unit exam. There are three or four balancing reactions, where it's just here's a reaction, fill in the blanks and balance it. Okay, and there are a couple of predict the products of a chemical reaction questions, and then there's some mole equation stuff. Okay, like it runs basically the same, it's just less than what you had on your unit exam. Yes. Just come in during a regular help time and you can do that. Okay, questions on that, on the naming? Okay, then we got to be able to write the formulas for both types of compounds. Writing the formulas for molecular compounds is super easy because it tells you what numbers to put in with the prefixes. Okay, so if I get this name here, if I get tetra carbon hexahydride, I guess, I don't know, I'm just making something up here, hexahydride, it's probably not even a thing, that's definitely not. Okay, what does tetra stand for? 4, okay, so this would be C4, and how many H's? 6, done. Okay, don't have to worry about swapping and dropping, it's a molecular compound, the prefixes tell me what numbers to write. Okay, now, in an ionic compound, if this was ionic, it's not, okay, what would I do with those two numbers? Reduce them. I don't do that for a molecular, but I do for an ionic compound, because the charges balance them. This one, the charges don't have to balance, everything's being shared, okay, so in molecular ones, we don't do that. Okay, and if I had, sorry, I gotta erase some of this now, I'm running that hard. If I had, let's see, sodium nitride, and I want to write the chemical formula for that. Okay, what would I do? What would I write first? Well, I'm sure somebody knows what I should write first. What does sodium look like? Na. Okay, what is sodium's charge? +1. Okay, and then I do the same thing with nitrogen. And then what do I do with those two little numbers I wrote? Drop and swap, right? Okay, so I bring the 3, I put it here, I bring the 1, we don't write 1s. Done. Na3N. Okay? What if I got something a bit more complex, like, like that one? Okay, well, I start out the same as I did for the other one. I write the prefix, or sorry, I write the symbol, and what's the 2 tell me?
It's charge.
It tells me the charge, right? Okay, so I go Ni2 plus. I do the same thing with phosphorus. It's a 3 minus, and now I drop and swap. I'm done. Okay, that's what the Roman numerals are for. They tell you which charge of the 2 possible charges to use in your drop and swap. Okay, is that ringing a bell? Do Roman numerals ever appear in a formula? They do not. Okay, that was a very common mistake on the unit exam. Okay, was people were putting formulas in, or sorry, Roman numerals in the formulas. Roman numerals have no place in the formula, only in the name. Sapphire, question?
If we were to like accidentally write down a Roman, could you?
I would probably be kind, but don't do that. I don't like being kind. Yeah, just don't do it, but I would probably. Okay, and then let's say toughest situation we could get would be this. Iron 3 carbonate. Okay, so I write the formula for iron, and what's its charge? 3, that's what the Roman numeral tells me. And then I gotta write carbonate. What's carbonate? CO3. Yeah, okay, so it's a polyatomic ion, CO3. And it has a -2 charge. Okay, so the reason I picked this is, first off, it makes us do another Roman numeral one. And secondly, what's gonna have to go around carbonate? Brackets. Okay, so if I drop and swap, the 2 is gonna go here, and the 3 is gonna go here. If I leave it that way, it's 2 irons, 1 carbon, and 33 oxygens. Not what happens, okay? This, however, is what happens. 1 iron and 3 carbonates. Okay, so the brackets are important as they really make it a lot different. Okay. All right, questions on the naming? We've now completely reviewed what took us like 4 days to do. 10 minutes. All right. So that's naming and writing formulas. That takes care of everything. Okay. Most important lesson, okay, or lessons in the chemistry unit. Lesson 12 and lesson 14. Okay. Those are the types of reactions, writing reactions, and predicting the products of a chemical reaction. Okay. I would say that that is probably one of the most weighted concepts on the final exam. Like, it probably comprises a double-digit percentage of the final exam. Okay? It's definitely more than 10% of the final. Pardon me?
Does it start with a Y?
No, it's not that high. I'm saying like it's like 10, 12%, something like that. It's significant. That's a lot for one concept, okay, on a final exam. So definitely review your reaction stuff. What are the 5 kinds of reactions?
There's an explosive one.
A Combustion.
Okay, combustion, that's the fiery one. It could be explosive. Okay, combustion, the fiery one. Don't write the fiery one or the explosive one on the test, okay?
Isn't there like a single one?
Okay, there's a single one. Again, single starts with R. Replacement, right. And a double replacement. Oh, see now, everyone's like, their memory is triggered. Okay, single replacement, in a good way though, not in a bad way. Double replacement. Okay, what else we got? Two more. Synthesis and decomposition. Okay, those are our 5 reaction types. There's a couple multiple choice questions about reaction types, okay? Like, which of the following, or this is an example of what kind of a reaction. A, synthesis, B, decomposition, C, combustion, D, double replacement.
On the final, is it gonna go like, it won't be like all over the place, like we'll start with like, let's say chemistry or
Yeah, it goes by order of unit. So even in the multiple choices, chemistry, bio, physics, global, and then in the written response, same thing. It's broken up by unit.
Is it close as the chemistry 25%?
They're not perfectly evenly weighted. Global is by far the least. I would say the other 3 are pretty close, but global would be less. So I haven't done the numbers, but my feeling on it would be that global systems is probably more like 15%, and then the other 3 would be weighted pretty equally after that. Okay. All right. So we'll go over some writing and predicting and balancing here in a few minutes, but obviously that's a pretty heavily weighted one. Okay. And the other main concept that we went over, okay, was the mole equation. Okay, being able to do mole equation calculations, okay, which again, we'll go over here in a few minutes. I have a couple of examples that we can go over, okay. So make sure you know how to use n equals little m over big M, or number of moles equals mass divided by molar mass, okay. And then you got Avogadro's number, okay. That is on your formula sheet. It's not something you have to memorize. 6.02 times 10 to the 23. Is the number of particles in a mole. Okay, those would be the really heavily weighted things, okay, that would be in the written response part of the final exam. Okay. Other things that are going to be on the final exam, like in the multiple choice part, could be lesson 4. Okay, so lesson 4 was properties of compounds. And we did a lab where we used the physical properties of a compound to determine its identity. So I would say expect to have a couple at least of multiple choice questions about that, where I probably ask you to do just that. So I might give you something like this. You have a blue crystalline solid that is highly soluble in water, whose solution conducts electricity, and the pH is 6.5. The possible identities for this would be A, iron 3 oxide, B, nitrogen triphosphide, C, copper 2 sulfate, D, cobalt 2 chloride. Which would it be? Copper. Copper's blue. Okay. We only really needed blue and crystalline to get that one, but okay, that's the kind of thing I might ask. Okay, give you a multiple choice question where you have to remember some of the properties of compounds. Okay, and use it just like you did in your lab. Okay, and lesson 8, solubility and the polar nature of water. So know the terminology. Okay, precipitates, right? Homogeneous, heterogeneous, your solute, solvents, okay, that kind of thing. Also be able to use your solubility chart. and be able to use it for a multiple choice question, where you actually had one of these on your unit exam as well. I gave you a chemical reaction, and I asked, which, if any, of the products would be soluble? Okay, so you look at the two products and you go, okay, sodium chloride, well, that's table salt. And when I look at my, periodic table, it shows that that is soluble. And the other one is magnesium hydroxide. And when I look at my solubility chart on my periodic table, I see that hydroxide is not soluble with magnesium, therefore sodium chloride is the only soluble compound. Okay, so you have like A, magnesium hydroxide, B, sodium chloride, D, neither, or C, neither, D, both, something like that. Okay, and so you have to use your periodic table and solubility chart to determine that. Okay, this is not one that you need to spend a ton of time on. It's one you need to read over. Okay, because there isn't really a lot to do with that one. Polar nature of water, there was a question about that on your unit exam. Okay, about why water does the things it does, because those hydrogen bonds, cohesion, adhesion, and then we came back to that when we were in the plant unit because it was what helped a plant transport water. Okay, so polar nature of water, it was in 2 units. Expect there's probably going to be a few multiple choice questions on that concept, so just have a quick read over polar molecules, what that means. Okay, charges aren't balanced, their electrons aren't shared equally, so one side gets charged and there's hydrogen bonds and that old chestnut. Okay. Okay, so yeah, we got it in the written response. You're gonna have balancing questions, as I said. Okay, I think it's 3 reactions. Okay, and it's just fill in the blank. Okay, so it's already written out. You just have to fill in the blanks, like 1, 2, 1, 2, or whatever. Okay, whatever it needs to be. And then you got 2 predict and balance questions. I think it's 2. Okay, and then you got some mole calculations. Okay, so just so you know, and maybe this can set your mind at ease a little bit. My philosophy on final exams is that they are not the place to ask the most difficult question I can think of, or give you the most difficult reaction to predict and balance. Okay? I believe that a final exam's difficulty comes from the volume of material on it, not from the level of difficulty of the questions. Okay, so I'm going to ask you exactly the same things I asked you on your unit exam. Okay, but they'll probably be at a slightly lower level of difficulty. But I'm asking you to demonstrate the same skills. Can you still do a mole equation calculation? Can you still predict and balance a chemical reaction? Okay, can you still figure out what's soluble and what's not soluble? Okay, those kinds of things. Those are going to be on there. They're the important skills you have to be able to demonstrate before you can move on to Chem 20. Okay, so that's what I'm going to ask. All right, everybody with me there? Okay, now I'm not saying that everybody has the same philosophy about their final exam. Right? Not everybody does that. I like to think of them as wrong, but that's their choice. Okay, some people think a final exam is the perfect place to ask the most difficult question they can think of. I'm not going to do that. Okay, I'm going to ask you to show me the same things I asked you to show me before. All right, so naming ionic and molecular compounds. Let's see if you guys can name those right now. So yes, you'll need your periodic table. Okay, I'll give you a couple minutes. See how we do with those, and then we'll do them up here. Mr. Schmidt, if you can please pause this and give the students a few minutes to try these, please. Okay, so we got our ionic one here. Okay, we've got MgCl2, so Mg stands for magnesium. Okay, and Cl stands for chlorine, so we're just going to change that to magnesium chloride. Okay, this one's molecular, so I need to put in the prefixes. Okay, we'll have dinitrogen, trioxide. Okay, questions on either of those? Okay, what's different about this one? Pardon me? There's more than one possible charge for iron, so the name is going to need a Roman numeral, right? Okay, so first off, I'm going to write the names of the two elements that are in it, iron and oxygen, so iron oxide. Okay, don't need prefixes because it's ionic, but I do need to figure out what the charge on iron is. So I always look to my non-metal to help me with that. The charge on oxygen is always -2. -2 times 3 is -6. So I've got 6 negative charges in this compound. It has to come out to 0. That means I've got to get 6 positive charges out of 2 iron atoms. 6 divided by 2 is 3. So the charge on iron is +3. So I put a Roman numeral 3 here. Now I have iron 3 oxide. Right, and then our last one here, okay, we've got sodium with carbonate. Okay, so it's an ionic compound. I just go sodium carbonate. I don't need any prefixes. I don't need any Roman numerals. Okay. Everybody all right with that one? All right, so we got a couple here now that we'll try. These are where we have to write the formulas for these. Okay, so Mr. Schmidt, can you pause this again and give the students a couple minutes to give these a try? All right, so for our first one here, okay, we got lithium nitride. So is that ionic or molecular? It's ionic. Okay, lithium is a metal, nitride is a non-metal. Okay, so I write the formula for lithium and its charge. I write the formula for nitrogen and its charge, and what do I do? Drop and swap, right? So Li3N is going to be my formula for lithium nitride. Okay, triphosphorus tetrabromide, ionic or molecular? It's molecular. It's 2 nonmetals and it has prefixes in it. Okay, triphosphorus, P3, tetrabromide, Br4. Okay. And then we've got magnesium oxide, okay, ionic or molecular? It's ionic, okay, so we got magnesium, I write its charge, 2+, oxygen, its charge, 2-. Those already work, so do I go 2 and 2 or I just leave it? Just leave it, okay, because we would reduce the 2 and 2 down to 1 and 1 anyway, okay, MgO. Very common mistake though to write the 2's, okay, just remember we always have to reduce. And then our last one here, we got copper 2 sulfate. What does the Roman numeral tell me about copper? Its charge, 2+. And it's with sulfate. That's SO4, polyatomic ion, which also has a 2 charge, but it's negative. Do I need to do anything here? Nope, it's already balanced. Do I need brackets? Nope, because I'm not writing any numbers beside that 4. Okay, CuSO4.
If you were to write brackets, even if it didn't need.
It's not technically wrong, but it's unnecessary. Yeah.
If you could do multiplication equations, just do brackets.
Yeah, exactly. Yeah, you wouldn't have to, right? Unless you needed to enclose it to have it done first. Right, you wouldn't do it. Okay. Any questions on those? Oh, I had another one. Nickel 2 hydroxide. We'll skip that because we did a few before. Okay, so let's have you guys balance these. Okay, see if you can put, and then I'll make a few where we have to actually predict the products. Okay, so right now let's just try balancing these 3 here. Okay, so Mr. Smith, you can pause it again. Okay, so we gotta, what are our rules when we're balancing? What do I start with? The highest number, yeah, okay? Unless it's a combustion reaction, those have their own rules, okay? But in this case, I should probably start with chlorine because it's the biggest number and it's obviously out of balance because there's only 1 over here. Okay, so I've got 2 chlorines on this side. What needs to go in front of the sodium? I need to put a 2 here. Now when I put that 2 here, it applies to everything. So now I've got 2 sodiums over here on the product side, but I only have 1 over here, so what needs to go here? Yeah, and now we're balanced. Okay, there's 2 of everything. That's about as easy as they get, other than having one that's already balanced. Okay. All right. The next one is a combustion reaction, and they're probably the toughest because they have their own set of rules. What were the rules? There were 2 of them.
Start with the 2 first.
Right, the rule of 2 is the second rule. If there's a, how do I know when to apply the rule of 2?
If it's an even number, and if the C's an even number.
Right, if there's an even number of carbons. So I would need the rule of 2 for this one. Okay, what's the other rule? What's the first rule? Go alphabetically, right. I always balance a combustion reaction in alphabetical order. Okay, so there's 4 carbons here. 2 times 2 is 4. Okay, so I'm going to need to put a 4 here to balance my carbons. H is next in the order. 2 times 6 is 12. So I've got to go over here, and 6 times 2 is 12. Now I can balance my oxygens, but I balance them from the product side where I've got numbers in front of both. Okay, so there are 6 oxygens here, plus another 8 here, for a total of 14 oxygens. What times 2 will give me 14? Balance. Done. Okay. All right, and then our third one here, we've got a double replacement reaction, lots of big numbers. What should I start with? Highest number, okay, but both sodium and magnesium are 3. When I have 2 that are the same number, I start with the one that has the biggest charge, because it has the biggest effect on the reaction. That means I start with magnesium because it's a 2+ charge. Okay, so on this side there are 3 magnesiums. I got to go over here and make sure there are 3 magnesiums. Okay, I have a bad feeling about this, but we're going to see how it goes. Okay, when I put that 3 there, okay, that gives me 3 oxygens. Let's see how this goes. I'm going to put a 3 here. Maybe it'll work. Okay, so now my oxygens are balanced. Usually they're the tricky one. Okay, so we might be okay. 3 times 2 is how many? Right, so I got 6 sodiums over here, so I need to put a 2 here to balance my sodiums. That gives me 2 nitrogens. All right, there's 2 nitrogens here. I think I got it. Okay, I think it worked out. I always worry when I have a 3, I have an odd number, because sometimes it doesn't work. Okay, so we got 3 magnesiums, 3 magnesiums, 3 oxygens, 6 sodiums, 6 sodiums, and 2 nitrogens and 2 nitrogens. So yes, it's good the way it's written. Okay, if this was fill in the blank, I would also put a 1 there. Okay, never leave a blank unless you really want it to mean 0. Okay, something to grab your phone. All right, any other questions on those? Okay, before we do mole equation, I'm going to write a couple of predict the products reactions. Okay, and we'll see what we remember for that. Okay, not there. Okay, here. So, write these ones down and give them a try. Let's say that. Okay, give me that one first. That is a tricky one to start with. I know it seems simple, but there's some things that we have to be mindful of in this one. All right, so I'll give you guys a couple of minutes to try that one on your own. Okay, reminder that when we're predicting the products of a chemical reaction, the first thing to do is identify what kind of reaction is going on. Okay, use that pattern to write the products, then drop and swap any ionic compounds, and check for special elements. Okay, something else to think about. Okay, so Mr. Schmidt, I'll get you to pause it, give you guys a couple minutes here. So for this one, okay, we've got iron, and it reacts with chlorine gas. What does chlorine gas look like? Cl2, it's one of our special elements. That's something that burns people if I put that question on there, okay? Or I put any of the special elements on there in word form. People forget, okay? All right. What kind of reaction is this? Synthesis, yeah. Okay, so in a synthesis reaction, the two elements are going to combine to form a single compound. So Fe is going to go with Cl. I got a problem here. Iron's got more than one possible charge. And because it was an element to start with, that charge is unknown. So what do I do?
When you take like the first one.
Exactly. I take the first one. It's the most common one. In this case, I have no way other than that to know what the charge on iron is. So I go with the most common, which is... Which one's first? 3. Okay. Sorry, I thought I heard it 2 others. I'm sure it was 3. Okay, 3 plus. This is a minus 1. Okay, so we're going to have FeCl3. Okay, that's going to be our final compound. And now we've got to balance. 3 is the highest number, so I've got to balance chlorine first. How do I balance 3 and 2? 6 is the lowest common multiple. So I'm going to put a 2 here and a 3 here. That'll give me 6 chlorines on each side. And then I need to put a 2 in front of the iron on this side. Now it's all balanced. Okay, questions on that one? Okay, let's try this one. Okay, I'll give you guys a couple minutes to try that one. Predict the products.
Where did the charge for chlorine go? Or
It was a minus 1. I just wrote minus,
oh,
so we don't write 1, so it came down over here. Yeah? All right, I'll give you guys a couple minutes on number 2 here. Okay, Mr. Schmidt will get you to pause it again. All right, so first off, what kind of reaction is this? It's a double replacement reaction. Okay, so in a double replacement reaction, the metals are going to switch partners. So on this side, I've got magnesium hydroxide. Okay, this is a +2. This is a -1. Okay, so I've got to drop and swap and put brackets around the magnesium hydroxide. Okay, it's reacting with sodium chloride, NaCl. This is a +1 and this is a -1, so it's good that way. Now, on this side, I have to make the metals switch partners. So that means that then magnesium will end up with chlorine and sodium will end up with hydroxide. Okay, what have I just made? I've made 2 ionic compounds, both of which need to be dropped and swapped. Okay, that's the next step. So this is a +2, this is a -1, so we got MgCl2. Okay, this is a +1, that's a -1, so that compound is fine the way it's written with no brackets and no numbers. All right, now I've got to balance the whole reaction. Both hydroxide and chlorine are present as a 2, so I'll just pick hydroxide because it's first. Okay, so there's 2 hydroxides on this side. Now there are 2 on that side. That gives me 2 sodiums. So I go back over here, make sure I've got 2 sodiums. That gives me 2 chlorines. There's already 2 chlorines on the product side right here. Okay, and there's 1 magnesium and 1 magnesium. So we're good. It's 1, 2, 1, 2. Okay. Questions on that one?
Does it matter if like MgCl, if they're like switch, so it's NaOH first?
Yep, that's fine. Yeah, if you have NaOH plus MgCl2, totally fine. The order makes no difference. Yeah. Okay, let's try another one here. Let's try this one. Okay, tricarbon octahydride burns in oxygen. Okay, I'll give you a couple minutes on that one. Mr. Schmidt, I'll have you pause it again. Okay, so I've got tricarbon hexahydride. Okay, so that's, or sorry, octahydride. So we've got C3H8, and it's reacting or burning with oxygen, which is the special element, O2. What kind of reaction is it? It's a combustion reaction. What are always the products of a combustion reaction? CO2 and H2O. All right, do I need both rules for balancing here? No. 3 is an odd number, so I don't need the rule of 2. I can start with a 1, but I am going to balance alphabetically. 3 carbons, 8 hydrogens, 4 times 2 is 8. Okay, and I've got 3 times 2 is 6 oxygens here, plus 4 more is 10. 5 times 2 is 10. Okay, we've got that one balanced. All right, let's try one more here. Okay, give you a couple minutes on that one. Chlorine is bubbled through a solution of nickel 2 nitride. So chlorine is a green gas, and they're just like bubbling it through. Okay, so letting the bubbles of chlorine pass through a solution of nickel 2 nitride. Okay, I'll give you a couple minutes on that one, and then we'll walk through it, and then we'll look quickly at some mole equation questions after that. So I'm only going to give you like 2 minutes to work on this one because we're starting to fall behind here. Okay, so Mr. Schmidt, about 2 minutes, please. So, for this last one here, okay, chlorine is a special element, so Cl2, that was the trick with this one, is bubbled through a solution of nickel 2 nitride. Okay, so nickel with the 2 plus charge, nitrogen with the 3 minus charge. Okay, so we got Ni3N2. Okay, what kind of reaction is this? Single replacement. Okay, so in a single replacement reaction, the element that is by itself is going to replace the part of the ionic compound that it's like. Since chlorine is a nonmetal, it's going to swap out with the nonmetal, so nitrogen will end up alone. Okay, so nickel will end up with chlorine, and nitrogen will wind up alone. Okay, the tough thing about single replacement reactions is you have to do everything. You have an ionic compound to drop and swap. This is a -1, and this is a +2 because the Roman numeral told me that. Okay, so we got NiCl2, and nitrogen is special. Comes as a 2. Okay, all these little things to check for if you're going to get this right. Okay, so now that I've got that written out, now I need to balance everything. Okay, so I'm looking at nickel probably first as it's the biggest number. Put a 3 here to balance the nickel. That gives me 6 chlorine, so a 3 here will balance that, and the nitrogens already work at 2 and 2, so I'm done. Okay, ringing a bell? All right, let's go back to some mole equation questions. Try this one. What's the mass of 11 moles of dinitrogen hexafluoride? Okay, I'll give you a couple minutes to try that one. Mr. Schmidt, a couple minutes, please. Okay, so we've got a mass, or we're looking for a little m. We know the number of moles, okay, it's 11. And we're told it's dinitrogen, so 2 nitrogens, hexafluoride, 6 fluorines. Okay, so we've got to figure out the molar mass of that by using our periodic table. There are 2 nitrogens, so 14.01 times 2. Okay, that's the atomic mass or molar mass of nitrogen. Plus fluorine is 19. Okay, and there are 6 of them. So when we put that all together, what do we get? Sorry, I forgot to start my calculator. It's going to take a couple seconds. Precious seconds.
We have 4 minutes.
But I have a lot to do. You guys are not helpful. Must I do everything?
My calculator is just too far.
Okay, so 28.02. okay, plus 19 times 6. We're looking at 142.02 grams per mole. Okay, and if we are now going to calculate mass, we have to manipulate the mole equation. So n equals little m over big M, multiply both sides by m. Okay, so we'll have our 142.02 times 11, okay, and that'll get us our overall mass. So 1562.22 grams. That would be our overall mass. Okay, now we haven't had a chance to do one that has. Oh, I've got the answer. Okay, let's just walk through this one because that's all we have time for. So if I'm looking for the mass and they give me the number of molecules, that's when I have to use Avogadro's number. Okay, or if they ask me to find the number of molecules, then I also have to use Avogadro's number. Okay, in this case, they gave me the number of molecules, so I'm going to first calculate the molar mass of hydrogen chloride, so that's just adding the two together, okay, and then I'm going to calculate the number of moles. I'm going to take the number of molecules and divide it by Avogadro's number. That gives me 4.153 moles. Then I can take that, put it in the mole equation, and solve for mass. So mass equals N times big M. Okay, it's something we can certainly go over more on Thursday. Okay, let's make a note of that. We're definitely going to do a couple more mole equation questions because we didn't get a lot of time today for that. All right. Can I scroll up a little bit? Is that enough? Oh, I was just kidding. I was trying to be a jerk.
Yeah, I wanted to, yeah.
Okay, there you go.